Now, when you're architecting a network, one of the things that you need to look at are your collision domains. And basically, if you have a specific subnet, if you have a segment of the network, the more nodes, the more computers that you put on that section, the more collisions that are going to take place, because there's more systems that have to communicate. And this is it's called contention. Contention means that different systems are competing for the same resource. So it'll be contention over that actual network link. All of us we only have one UTP line to communicate over, so the more that you put on that line, the more collisions that are going to take place, which reduces the performance of your network. And again, the systems will have to resend after a collision happens. Now, what happens is each system can determine, or they can hear, that a collision happened, because when the different types of data, because remember it's electricity, when they come together, they actually increase the voltage and it goes over a certain threshold. And the systems around, if it detects that a certain threshold has been hit, a voltage threshold, that tells the system, hey, there's been a collision. Now, so it backs off. It says, hey, there's been some type, they're having collision issues, I'm going to back off, give them time to work it out, and then I'll come back to the wire and put my data on. But what if we all the systems backed off and then they all came back to the network at the same time? Well, that would make a lot of sense, because that would actually increase the potential for collisions. So the drivers in the network stack have a algorithm that means that when there's a collision that's detected, it'll be a random number on when this system comes back to the network line. This one will come back at a different time. So instead of them all coming back to the actual UTP line, they come back randomly. And again, it's all about trying to reduce the amount of collisions that happen. Now, a common way to deal with collisions, it's called CSMA, Carrier Sense Multiple Access. And there's two actually flavors of CSMA. There's CD, which is collision detection, and there's CA, which we'll talk about. Now, CD, really what it means is that before my system is going to put something on the line, it's going to listen and see if it's busy. If there's actually data going on, I can't send yet. My system will listen again, free, okay, send the data. And that's what Ethernet uses. Ethernet uses CSMA CD. And a lot of times collisions happen because when it listens to see if the line's free, it can only determine for a certain period of time. It can't detect maybe a collision that happened way down the line. It's too far away. So CSMA CD is very common. It's implemented in Ethernet. And again, the whole goal is to try to reduce the amount of collisions that happen. Now, CSMA CA is collision avoidance. Now, where the other one is collision detection, this is collision avoidance. And this is what 802.11 uses. It uses a lot of, there's a lot of similarities between Ethernet and 802.11, but one of its differences is how it tries to avoid collisions. What this will do is it'll listen to see if the line's free, and then it's going to put a packet or a frame on the frequencies to basically tell everybody else, okay, I'm going to talk, so don't you talk. And then I'm going to put my data on the radio frequency to go wherever it needs to. And so the different devices that it has received my packet are basically going to randomly come back for communication. So where CD just listens to see if the line is free, CA will listen, and it'll send out a message basically saying, everybody shut up right now because I'm going to talk. And then when another system needs to communicate, it will do the same thing. It will see if the line's clear, and then it'll send a packet, and then it'll put its data on the line. So Ethernet it's really won the war. We've had a lot of technologies and protocols that have been used over the years, and a lot of times you don't know which is going to win the war. Ethernet definitely did over Token Ring. Token Ring can only go up to 16 bytes per second, or bits per second, and Ethernet has continuously been able to go up and up and up into actual gigabytes. So Ethernet has the flexibility to be able to allow more and more data throughput. Now, there's actually a difference between bandwidth and data throughput. Bandwidth is the pipe, is how much data that can go through. We have baseband and broadband, but the data throughput doesn't always equal the bandwidth. It could be that's an old wire that actually there's like interference going around it, and that could reduce the data throughput. But one of the things with Ethernet is that it's able to shove the same amount of data and get up to gigabytes over a copper wire, because it's using an algorithm to actually compress the data. So Ethernet has definitely won the war in what we use in a LAN environment, and it's called a chatty protocol because all the systems are in contention. They're competing over that line, UTP or STP or fiber. They're all competing over this one communication channel, and so it's called chatty, and it has more collisions than any of the other LAN type of protocols that we'll look at. But the reason it won is because of the speed, because we're up to like gigabytes throughput speeds. Now, another approach to dealing with how systems communicate and how we try to ensure that collisions don't take place is called token passing. And token passing, we have different technologies. There's Token Ring, there's ArcNet, which did not win any war. It's dead. We don't use that anymore. FDDI. These are technologies that use token passing. And the architecture that's set up, the physical topology, is a star. Even though it's called a ring, the ring is at the data link layer. The physical topology is a star. So this central device is called the MAU, the Multi-Station Access Unit, and all the other systems are connected to it. Now, where the ring comes in is that there's a logical ring within the central device, and so there's a token, and what the token is, it's actually an empty frame, and no computer can put any data on the line unless it has a token. So when it goes, the frame, the token will go up to this system. If it has nothing to say, the token goes back empty onto the line. It goes up to this system. Now this system has data to put on the network. So what it does is it puts its data on, it changes that token to the address of where it needs to go. Then the data is put on the line, it goes to the destination. The destination system will make a copy of the data. It doesn't actually take it off the line and delete it. It copies the data. It basically switches a bit within the token that says now it's free. Or that bit switch says, I got it. So again, the sender will basically change the token with a bit saying it's going somewhere and it's got some data. It goes around the line. The receiver changes a bit on the token saying, I got it. But that data goes all the way back to who sent it, and then it will take it off the line. So you see how, since all systems can't communicate at the same time, yeah, there's no collisions. That's great. But it's slow. If only one system can communicate at the time, it's very slow throughput. But it's not just Token Ring that uses token passing technology. Token Ring is one LAN protocol, and its standard is the 802.5. So again, some people get confused about the physical ring versus the logical ring. There's definitely a difference. A logical ring will happen within the device, and sometimes it's called a collapsed ring, and that's where the ring actually is, because it'll go out and say, do you need anything to say? No. Do you need anything to say? No. Do you need anything to say? So it's going in this circular motion. But usually the actual physical topology would be a star, because it has a central device that's actually keeping track of that token, and to make sure that there's always a token, make sure there's not two tokens. So I said that other technologies use token passing. And we're going to look at FDDI a little bit more when we get into the MAN technologies. FDDI has been used as a backbone technology in LAN environments for a long time. It's not used as much anymore because Ethernet has actually hit the same gigabyte throughput, the FDDI. But FDDI is used as a backbone within a LAN, or it can go over a MAN, metropolitan area network. And it does the same thing. It has a token. It actually has two tokens to allow two computers to communicate. And then, so there's FDDI, which goes over, that carries data. And then there's FDDI 2, version 2, which allows to move other types of data, voice data, video data. And as I said, ArcNet is another technology that uses token passing, but it's done. We don't use it anymore. So the last data link communication method we'll look at is called polling. Polling isn't as popular or used as much as the other ones that we talked about. In mainframes, that's where polling is usually used. And what this means is that you have a primary system that polls, asks secondary systems, do you have anything to say? Then it goes to another one, do you have anything to say? Do you have anything to say? So this primary system is controlling when the secondary systems can actually put data online or communicate. Again, this isn't used like necessarily in our network LAN environments. It would be more of communication with a mainframe, or if you had more than one mainframe that needs to communicate. And that type of polling is built on protocols that use SDLC, HDLC, which we're actually going to get a little bit deeper into in this domain.